Hello, you are now listening to the Modem Podcast, where we deconstruct, examine, and discuss deeply technical data networking and information technology topics. Sit back and relax while we fire up Dial D and the 9600 baud modem and connect to the Wildcat BBS.
All right. So welcome to another episode of the Modem Podcast. Today, I think we're going to talk about something pretty interesting for everybody. We should all know how important things like configuration management, change tracking can be for running any kind of production network. And there are a number of different ways to accomplish this, obviously. For anyone that's looked under the hood at how open source tools do their jobs, it's pretty clear that there's been a fair bit of work at understanding how to not just access, but also interpret the output that they're consuming. So getting into a device, running commands, or touching its API and telling it the information that you want it to consume. But how this is done over time, how these tools keep up with the constant churn of changing APIs and CLIs and interface changes and software updates, command sets, emerging software, all of that stuff that we have to deal with on a day-to-day basis. How does it do that? That's a hard problem to solve. And today we're going to look behind the curtain at how Unimus, which is a flexible configuration management and automation engine, keeps cool and calm under the pressure of constant change, and how they adapt and extend the large number of devices that they support. With us today, we're going to talk to Tomas Kirnak of Unimus. And with me to keep me on track and focused is Chris Cummings and John Osmond. Chris, John, how you guys doing today?
Doing all right. Thanks, Nick.
We are surviving.
All right. Tomas, so this is some pretty cool stuff. Can you sort of set the stage and give us an executive summary of what Unimus is, how it started, how it's evolved over its lifespan?
So maybe I'll start with how it started. And basically, I was a network engineer and then a network architect for about 15 years. And so when I quit my last job, I sort of wanted a little bit of change. After 15 years, you kind of wander into different technologies and different fields. So basically, I took half a year off and basically learned Java, which is a programming language. And so after that half a year of learning and experimenting with the programming language, I decided I would write something that I myself was missing in our industry, right? And that's something which I slowly wrote out. And then I had a couple more senior programmers join me, and now we are an entire company. So that something became Unimus. And from the beginning, the idea was, software exists to help us, right? You should never have to fight with software. It should help you do your job. It should empower you to do the things you want to do easier. And in this area, in network automation, network configuration management, the softwares that exist are super complicated. And so the entire idea behind Unimus is this should be simple. It should be easy to do. It should be fast to pick up. It should just work. And so Unimus became a automation and configuration management tool that hopefully does that.
So that's an interesting point there, if I may jump in a bit, because I have actually used Unimus in the past, and that's one of the things I like the most about it. That is that it's user friendly, but then I also heard you say something that maybe triggers something deep inside of me. Java. So you're using Java and you're making a human usable program. I'd like to maybe kind of hear a little bit about what steps did you take to make Unimus something that's easy to use, but you wrote it in a language that traditionally gets a lot of flack because it seems like everyone has a memory of using a horrible application that was, written in Java.
So I think, and this is a common reaction we get, like, Java, why? And so programming language in reality to the user experience doesn't matter, because you can do stupid stuff in any programming language, right? The programming language is just a tool you use to express what the software should look like. And of course, yeah, that's a loaded statement because there is a big difference if you are using like Bash, which is really a scripting language, interpreted language, versus Java versus Python, which are completely different languages, which have different structures, different syntaxes. But if you look at it from the user's standpoint, the ease of use, the usability, the user experience, and everything else, that is really not about the programming language, right? It's about the architecture, about the design, both the of how the infrastructurally, if that's a word, how the software fits into your network, how you install it, how you maintain it, how it communicates with external stuff, all the way to the front end, how the user experience is designed. And all of those really don't have anything to do with the programming language. So Java is a really good programming language, actually. So Netflix, the entire backend of Netflix runs on Java. I think the last I heard, they run like 400,000 instances of JVM, the Java virtual machine, which is insane. So if you think about it, if it's good enough for Netflix, then it's good enough for just about anything. The question is how you use it and how you package and deploy it to the user, which sadly here is where Java gets a lot of flack, because Java is such a powerful and easy programming language that people have misused it a lot in the past, and it gets a really bad image in the industry. But really, if you do things properly, it doesn't matter if it's Java or Python to the end user. Of course, to the programmer, it matters.
Yeah, I had a similar reaction the first time I played around with it. I was like, because 20 years ago, a Java application, you had a lot less memory to work with, and again, it was sort of early days in that, and you had these problems that you may run into that are typically resource related. But once I started messing around with it, with Unimus in particular, because I've played around with it as well, I realized like this is really low footprint, like incredibly low footprint. Like mine ran on a Raspberry Pi for like 2 years with plenty of overhead left over. So I think that's a very good point that, and I don't want to get too hung up on the Java pieces of the programming language, but I think it's a good point that to make that, the tools are only as good as the person that is wielding the tool.
Indeed. I've been having a hard time dealing with software that doesn't have a make install set up, and as time is going on, the people that are putting this software out here are getting much better at it, even if they aren't using the traditional tools that we're used to seeing.
Yeah, for sure. Okay, so we've established sort of what this does, and I think people understand what the usefulness is of these tools, because anyone that's ever had a device crash or otherwise fail that they needed to restore the configuration of, having some sort of a system in place that does regular collection, and ideally it'll tell you what the differences are and things like that on a regular basis, understands that they are worth their weight in gold. Having written a handful of modules for Rancid over the past way longer than I care to admit, I get how useful it is, and two, how difficult it can be to deal with some of the more esoteric hardware that's out there. But I think the thing that's really interesting to me about this is the behavior tree stuff that you're doing on the back end, because what I realized not only when I started messing around with this was that the footprint was really small, but like if it could talk to a huge number of devices with zero effort whatsoever. It was a eye-watering number of devices that this supported just right out of the box with no change, no tweaking, no configuration. And I thought to myself, somebody has put a heck of a lot of work into the back end of this to make sure that not only these things work when a user tries to plug in a piece of they plug in an address that's a piece of hardware. You don't even have to tell it what that hardware is. You just say, here's an address. Go figure out what this is, do a discovery, grab the config, and then you're done. And so the amount of work that had to have been done to sort of glaze over that from the end user experience, I knew had to be significant. So long time ago, probably a year ago, I would say, Tomas, I was asking, hey, we should talk about this, because I think that this is the man behind the curtain on something that's very complex and very cool, but nobody gets to see it. They see the benefit of it, but they don't actually get to see how and hear about how it's done. So I'm gonna be quiet for a minute, and I want you to sort of guide us through some of the, the entryway into how this is done.
Yeah, so maybe again from like historically, as I mentioned from the beginning, the idea about Unimus was it should be as simple as possible. It should just work. And to me, a big part of that is that, and with all other solutions currently there are, you have to tell it what it is talking to. Here's the username, here's the password, here's the model, here's the vendor, here's this, here's that. And as soon as you change something in your network, then suddenly you have to change everything else in your tools, right? And to me, that's just not scalable. That doesn't work. So from the start, Unimus was designed to only get an IP address, and without any other information about the device, be able to completely discover it, communicate with it, and deal with it. And that was the driver behind all of this backend technology and all of this development that we have done, which we will now talk about. So if you think about it, there are basically, if you think about device management, there are, I don't want to say strictly two types of interfaces, but generally speaking, there are human-centric interfaces and then there are machine-centric interfaces. So your usual API, a RESTful API is a machine-centric interface. Why? Because it uses standardized technologies, of course, like HTTP. Then you have data formatting models or methods like XML or JSON, etc. But really, to humans, that's not a good way to represent things, as probably anyone that has looked at the big XML or JSON sheet knows, right? To us, it's structured data, but not really for us. Whereas a CLI really is a human-centric interface because it is built to be interacted by humans, not by machines, mostly. Again, that statement is a little bit loaded, but it is built for humans, right? There are no rules. Every single CLI is different. The syntax is different. The data formats are different. And this is the problem behind standardization of software tools in the networking industry, because every single vendor does something completely else and their own proprietary, right, with the CLI. So from the start, we did not want to focus on those machine-centric interfaces. Why? Well, because we humans, or if you think about it, network engineers already know a configuration language. It's the CLI. Of course, that configuration language is different for every vendor. But if you think about it, we all already know this configuration language for the equipment that we manage. We've already learned that, and we deal with it on a daily basis. And to me, it's a little bit backwards that network engineers should now learn a programming language. So, for example, Python. Then they should learn some templating language like Jinja or Yang. Then we should learn data representation, models and all of this. Like that is so much work. It's hard enough just keeping up as a network engineer, right? So we took that as a fundamental fact that we already, all of us know how to interact with the CLI, and it is a configuration language. So let's just use that. Because if we use that, then all of us can immediately pick up this tool and be able to configure anything we want with it in our network. And this approach has, of course, benefits and pros and cons, but it's the best approach if you want to have things done very fast and quickly and the software be user-friendly. So I think I've sidetracked a bit, but that was the driving force behind sticking to the CLI and basically programming against a human-centric interface versus a machine-centric interface. So when we get back to the backend and programming, it's a completely different paradigm, because now you can't think as a software developer. You can't think as a programmer, because the interface you are programming against is not a machine-centric interface. So you really have to switch your mindset to how does a human think and how does the human brain and our pattern recognitions that are in the brain of all of us work for us to be able to just come into an empty CLI and immediately know, oh, how do we know how to deal with it? How do we react to all of the different questions and prompts and conditions that can happen in this human-centric CLI? And so we are getting closer and closer to these behavioral trees, which you mentioned. So how did we choose behavioral trees as the right way was actually, again, if you think about it, what is a CLI? Really, it's a puzzle. It's a closed system, so there is a syntax to it, as we mentioned, it's a configuration language, and there is a limited set of options. It's not unlimited. You are limited by the possibilities, by the keywords and commands of the CLI. So it really is a puzzle of I want to achieve something. Here are some possible options of how to do many different things. How do you get to the right thing which you want to do? So this CLI is a big set of tools and possibilities that have many possible outcomes, and we want to get to one of these outcomes. And if you think about it a little bit more, it gets really close to what we have in games, in gaming, in computer games. So what happens in a computer game, as probably most of us in this industry have played the game at some point. If you think about some, RTS, real-time strategy games, those can be also really complex but limited systems, right? You have a certain set of rules, certain things can happen, and basically the branching of these simple things into more complex things goes on with time. The deeper you get into the systems, the deeper the parts interact with each other, the more outcomes there can be. So, but it's also a puzzle. A game really is a puzzle, right? You have many tools and you want a certain outcome, whether that's beating your opponent or building the best city in like the city builder games, etc. And in games, there already are AIs, and I really hate the word AI because it has become a blanket term that means everything and therefore means nothing today. But your game opponents are AIs, and these game AIs have existed for 40 years, more, definitely more, but in a serious state, right? And so if you think about it, it's very similar, because if you come into an empty game, it's a blank canvas where there are many possibilities with a limited set of tools. If you come into a device CLI, it's a blank CLI, and there are many possibilities and there are many possible ways to do things, and you want to achieve a certain outcome. So how do AIs work in games, and how are they able to basically from this limited and set of rules achieve outcomes and achieve behaviors? Is using what's called a behavioral tree AI. So we utilize this context or this philosophy, this technique in Unimus as well, and we basically build out a behavioral tree AI. Again, I hate the word AI because it's very different if it's a deep learning, it's a GAN AI, it's all of the AI. There are many different types of AIs, and people, assume a certain thing when they hear AI. In Unimus,
so let's touch on that a little bit, because I think that is an overused word, and it reminds me of what SDN was 10 years ago. But I think you've talked about the behavioral tree, and from what I understand about it, which is admittedly not a huge amount, but you've kind of gone over this a little bit, but I want to dig a little bit deeper. So my understanding is that a behavioral tree is a way to set a bunch of small tasks into a modular fashion that gives you an outcome of some kind. It's a way to make complex things more simple by breaking them down into these smaller tasks. And without having to sort of think about how the tasks are each individual task is implemented. So what you're saying is you worry about this thing, and then when this thing's done, you worry about this thing based on the answer from the thing before it, and you use that as a building block for whatever that path is. I think about it more like a path than a tree, which is probably not right, but it's a way of breaking things down into simple tasks is my sort of caveman understanding of what this behavioral tree AI stuff is. Is that, how accurate is that?
It's a part of it, but it's just a part of it. So a behavioral tree, a path, or what you described, a path would be a task. So this would be going from nothing to achieving a certain goal. That's a task, right? And the task is comprised of many behaviors, and the behaviors link to each other. So this path that you describe on is just one possible task, is just one possible path in a large tree of possible behaviors, right? And the magic with behavioral trees is that you start from a central single point, and then the tree has many possible branches or paths that can be taken within the tree. And depending on external inputs, so in a game, this would be, the behavior of your opponent, if you are looking at it from the AI's point of view. And in Unimus, this would be the behavior of the device. So depending on what's happening at each decision point within the behavioral tree, a different branching path within the behavioral tree will be taken, all the way up to a specific exit point or a specific result. And that result can be positive or negative. It can be something succeeded or something failed. But if you think about it, it's a huge tree of possible paths, and the job of the AI is to find the right path in the tree by whereas on each decision point you take the path one step forward, so to speak.
Okay, so let me break this down into what I think an engineer would see. You run what's going to happen when an engineer performs a task, right? Because this is all obfuscated on the back end, right? As it should be. An IP address is inserted into the platform. The platform then has been configured to say, I understand SSH and Telnet, let's just say, right? It's going to try both of those in a specific order. If one succeeds, it will move to the next step. Let's say SSH works because, as we all know, you probably shouldn't have Telnet enabled because it's 2021. And SSH succeeds. Then it goes to the next step, which is I need to check for credentials. And you've put in some credentials that, a set of them, or maybe just one. But if there's a set of them, it will try that first set of credentials. If that doesn't work, it moves to the second set of credentials. If that one works, it allows access into the network element. Then it starts trying to figure out what that network element is, and it will run commands, show commands, or what happens at that point? Is this on track?
So yes, that is very on track, although it's very simplified, as it probably should be.
I don't do it any other way.
So these steps that you described so far are easy. Why? Because opening a socket and checking if it's opened, super easy, right? Then opening a certain standardized protocol like Telnet or SSH of that socket, super easy, right? Checking credentials, that gets a little bit more complicated because SSH has credential validation built in. It's a part of the protocol. But Telnet, it doesn't. It's a wild, wild west. Basically, you open a Telnet session and you have no idea what data will be coming in. So for example, even for Telnet, just logging into the device is much harder than you would think. For SSH, it's easy. It's a standardized part of the protocol. So actually, the first part of the behavioral tree already has to know and understand in this branching path, is this a Telnet connection or an SSH connection? If it's an SSH connection, a different path in the behavioral tree will be taken, whereas it's a Telnet connection. Because Telnet connections require very different login behaviors than SSH. And you will see that I use the word behavior here a lot, and we can get to that a little bit in a little bit.
Tomas, when you're talking about the Telnet piece here, I'm just curious, do you collect any data, say in the Telnet piece, that gives you a clue of how to use things further down the path on certain pieces of equipment and things like that?
Oh, yeah,
or
definitely.
Is it compartmentalized?
Each step of the behavioral tree collects data which is used by later steps. As an example, SSH server thumbprint, SSH server version, can already tell you if it's a Cisco device or a different device. So this data is, of course, stored, and later on in the decision path within the behavioral tree, this data from previous steps can be used, definitely. And same with telnet, same with like login banners. Basically, all of the previous steps within the behavioral tree, the current decision point can use data, or really it sees the path. Realistically, it sees the path, and depending on what has been happening in the previous path, can and often does influence the decision where the path inside of the behavioral tree continues.
So, how does this differ from, traditional if-then logic in a programming language? Because as a network engineer, I'm, not a programmer, just very rudimentary level, but, I kind of just know how to do what I need to do to get the job done. And I've often found myself, at least, early on, building long 20 deep if-then just atrocities that, are no good and no seasoned programmer would ever make. So how does the behavioral tree really differ from that hideous long chain of nested if-then logic?
So if-then is just a basic expression of a programming language. It's just some decision logic, right? And you can use it or you can abuse it with a 20 deep if statement, right? So really the problem with this is that, and as soon as, again, I don't want to say absolute statements, because absolute statements are never right. But any serious programming language or a serious programmer should never write a class or a method or a function that's like 800 lines long. Code should be very compartmentalized, so it can be easily tested, so it can be easily understandable. Basically, the complexity of the code path should never exceed a certain number. So building these huge branching if-else statements are extremely difficult to understand, extremely difficult to debug, and even extremely difficult to properly cover them with tests. So all the possible code paths, covering them in tests is very hard. So the behavioral tree really is a way of organizing code and organizing the different responsibilities of the code, like Nick mentioned in the beginning, into very simple tasks that are easy to execute, easy to debug, easy to test, and then building bigger behaviors out of simple algorithms, you could say. So it's like complexity emerging out of simple things. So in the end, yeah, there is a big complex behavioral tree, but the point is, you can very easily see the totality. It's called a state space of the behavioral tree, because it is so what we use in Unimus, to be more precise, is an undeterministic finite behavioral tree. But the word finite is very important, because that means that you can actually understand and you know all the possible code paths and all the possible behaviors within the behavioral tree, which makes it much nicer to be able to know which part of the code base is covered by tests, which isn't, which behaviors, when they happen, how they happen, are we testing for it, does this behave as we expect it to? If something doesn't work, you don't have to debug a 800 long lines if-else chain, you just debug individual simple behaviors.
Okay, I'm thinking that anytime you're at a given node in a tree, you've already got, that gives you the set of assumptions of what if-thens have already been, formed and found, and what's true and what isn't.
Yeah. With a lot of metadata and stuff like
that. But the piece that I'm kind of wondering now is, now that you're saying this, I hadn't thought about this before. How much of the tree is driven by a vendor's given CLI, and how much of it is driven by your intent to put anything in place on a given piece of equipment? Generically, I want to set a route, or I want to look and see the way things are done, and that's in that nature. I'm thinking ahead into some of the automation pieces that have been going on, but I'm seeing two different lines that could be taken here, and I'm kind of curious where Unimus takes that, or where you're prompted from.
So in Unimus, so we have what are called vendor drivers, and we build a driver for every single piece of equipment that we support. So currently we support some 190 different device types, which means we have 190 plus drivers. And so the behavioral tree logic is completely driver independent. And really, for each driver, a certain part of the behavioral tree can repeat and test individual drivers during discovery. So if you are talking about the automation features, the nice thing about automation is that you already know exactly what you are talking to, because in Unimus, you can only perform automation config push on devices which have been discovered. So at the point where you want to do config push, Unimus already knows exactly what the device type and vendor and model is. Therefore, it has a single driver which claims that device. And therefore, the behavioral tree can skip a lot of like the previous discovery nodes and figuring different things out, because the driver already tells it what to do. But the behavioral tree is completely driver independent. So you can basically, writing a driver for us, it's completely separate thing from adjusting the behavioral tree and the individual behaviors. I hope that makes sense.
Very helpful.
So yeah, I think we were saying and talking about state space, and so as I mentioned, Unimus uses a non-deterministic or undeterministic finite behavioral tree. Which means that, and this ties also into state machines, because Unimus uses multiple state machines within that behavioral tree. So we have, I think, 3 most important state machines, which would be the device login state machine, which is I think that one has about 200 possible code paths that it can take. So the state space for the login state machine is about 200 different paths through the state machine, through the behavioral tree of the state machine. Then we have the mode change state machine. So this is when you come into a device and you do enable. And actually, you would be surprised how many different things can happen when you just type in enable. Like, the possibilities are much larger, especially if we are talking about supporting 190 vendors. There are many things that can happen, and you have to deal with this. So the mode change state machine, I think, is a little bit smaller than the login state machine. I think that one has like 180. The state space is 180 different code paths down that state machine. And then we have a discovery state machine, which is a more encompassing state machine, because the discovery state machine encompasses the mode change state machine. So during device discovery, you want to discover, if it even has modes, because many vendors don't have modes. Some vendors do, and if they do, can you get into them? Do you have proper credentials to switch modes, or you don't? Or you might have multiple possible, mode change passwords, which need to be tried and tested. And some devices can only be discovered in certain modes. So if you log into a Cisco and you log into base mode, user exec, it's possible you don't have privileges to do show version, right? So the driver must be able to discover the device in base mode, and if that doesn't work, you need to switch into enable mode, and the driver needs to be retried, because maybe your user only has privileges to do show version in enable mode. And so all of these behaviors and all of these possibilities are encompassed inside of this behavioral tree, which has to be able to deal with all of this.
Yeah, the thing that always stuck out to me when I was doing, work on Rancid and writing the modules for that was that the prompt changes varied so widely
for a long time.
Right. I mean, you're dealing with not only prompt changes when you may go from privileged to unprivileged mode, but some devices may have prompt changes when you have uncommitted changes or unsaved changes, depending on what the platform is, and they may use strange characters in there that are hard to escape. I mean, this is a non-trivial task to accomplish for one device. So having to scroll through that, having to work through that tree for however many devices that are supported is, I don't see any other way you can do it in a timely fashion if you don't use some sort of logic in there, because it took me like a day to figure out the regular expressions for certain vendors that did some strange things with not strange things I did not expect with the prompt. Right now, granted, that isn't my core competency, but still, I mean, it's that I think that particular task by itself is much more difficult than a lot of folks maybe realize. It's there's some black magic happening behind there for folks that don't really have any background in that type of skill set.
So we have a entire set of behaviors in the behavioral tree just to learn the prompt to be able to identify it in later communication. Because you can have banners in devices, and if you do show running config, the prompt can easily be a part of your output. So Unimus has to be really certain that it can when it can interact with the device and when it can't, because you can't interact with it if it's outputting stuff, and then if you interact with it, it will output what you typed in after the prompt, and you might desynchronize the entire communication. And this is the thing that I mentioned, like, you have to think like a human. How does a human know when you can interact with the device? How do you recognize the prompt versus the same words inside of a banner versus the same words being displayed when you are outputting show running config, or where you are running some arbitrary configuration push? So this is the nice part about the behavioral tree, that you can encompass these learning behaviors as an early part of the behavioral tree. And like we mentioned, later on, the later decision steps inside of the behavioral tree can use this, this learned information from the previous communication in their decision points.
So I want to highlight that a little bit, because given we're talking about this behavioral tree, right? So this is a process that collects this data, and I think it's key to understand that it's going to reuse some of this data to make life easier going forward. So if you contrast a behavioral tree that is able to sort of harvest information about what it's doing with a static, here's the address of this network element, here's the login in a flat configuration file, and you need to tell it, oh, type is, vendor X, and here's the login, enable 1 or 0, and this is how you talk to this device. That's very, very static. That is the static routing of pulling down a configuration, because if that device changes in any way, if you change the credentials, if you change the IP addresses, if you change the vendor, and I've seen in the past, if you change certain things about the actual operating system, going from different versions of operating system can even affect this, then you have to go back in and actually touch that flat configuration file, because it's very likely, in any of the open source options that are out there, it's a flat configuration file. And again, I'm not disparaging any of that, because I've used those extensively, and they've saved my bacon more times than I could count. But that behavior tree here that we're talking about, collecting that information and understanding what it's actually doing and being able to go back and reference that and then rediscover if it needs to, I think is really the secret sauce here.
Well, as I mentioned, if you think about it, it is an AI, it is intelligent in a way. It's not sentient, it's intelligent. But if you think about going back to those games, it's the same thing that those game AIs have had to do for the last 40 years. They have to react to changing conditions. They have to be able to react to unexpected stuff, and it's the same concept, right? Behavioral tree AIs are very good at dealing with known conditions, but in a completely undeterministic ways and sequences, right? So this is why I mentioned that it's a non-deterministic finite behavioral tree, because the CLI is finite. as we mentioned before, syntax, keywords, those don't change. So yeah, it's the intelligence or the I suppose it just can react to change very nicely, and it's a very different approach than static code. Yeah.
So, an example of like reacting to change would maybe be then thinking of something like Rancid, where if you replaced an iOS router with an iOS XR router, in Rancid, you'd have to go in and change, just like Nick said, that static configuration file and go, okay, now I have to tell it this is an iOS XR router. But with Unimus and with this behavioral tree, Unimus is able to go on the fly and say, okay, I'm now aware that this is a new way of interacting with the same device. And then you as the engineer don't actually have to go in and actually make any changes on your backup tool because Unimus is taking care of that for you. That's kind of what's going on, right?
Yeah, it is able to deal with unknowns, whereas a static definition in Rancid or Oxidized is not. So even if you think about it, if you do enable, it might ask for password or it might not, or it might ask for a username and then password, right? And so specifying all of this manually, and then suddenly you change something on your TACAX server and it breaks everything. With Unimus, it just keeps on working.
Right. So specifically, the behavioral AI tree on the back end is handling those changes that would normally be a human interface to go in and manually touch something. So we talked about how this behavioral AI tree is able to sort of understand and adapt as it needs to. Let's talk about the scale, like the scaling, right? Because we've discussed some pretty complex concepts here. And there are people that run very large networks, and given the complexity of what's happening on the back end and the number of devices that are potentially out there, like what type of scaling issues have you seen? Like how big have you scaled this?
So the largest customer we have right now is running 18,000 devices in a single Unimus instance.
Oh, wow. That is a lot. That's
Wow.
cool.
It's a fair few. That's a fair bit of devices. Wow. And they're running this on, just like a bare metal machine, or is it running in virtualized? Is it running in Docker?
Yeah, it's running virtualized, not bare metal. And actually, funnily enough, the highest load is on the database server, not on Unimus itself.
Yeah, because there's a back-end database that it stores all of these things in, encrypted as well, right?
Yeah, so everything Unimus does is encrypted in the database. And this is very simple. If you are in a big network and you have a database administrator team and you have a network administrator team, there is no reason that the database admins should be able to open the database and see your enable passwords and your login passwords and all of this, right? That just doesn't make sense. So Unimus encrypts all data on the application layer. So if somebody opens the database, they have no idea what they are looking at. It's encrypted using AES 128.
So you're talking about some of the components of Unimus. Obviously, the behavioral tree is one of them, but the components required to scale this. And of course, you mentioned a database server with DBAs maintaining it. Now, when I've run Unimus before, it was just installed all in one box. But the components of this software, are they able to be broken out and even the parts of the software that performs the login to your network device? So, are those all coming from one central server, logging into your network devices, grabbing the information that Unimus needs, or can you spread that load out horizontally, or even do network segmentation reasons? Are you able to put those probes elsewhere in the network? Can you break this down into smaller pieces?
Yeah, definitely. So Unimus can be scaled both horizontally and vertically. So like I mentioned, the one biggest customer, it's all in a single instance, but you can actually break down Unimus into, you have a separate database server, a separate application server, and then 10 pollers. Sure, you can. Or going back to software should be simple. If you don't want to deal with any of this, you can just run everything in one, right? The database, application, and polling, all of this can be just run off one machine, and you don't even have to use like a serious database server because we support file-based databases. So it's just a file on the file system. So you don't even have to install like MySQL or Postgre. But of course, we don't support that for large installations, because for large installations, you need an actual database server. A file system won't work with 18,000 concurrent jobs.
And you can actually run this as a Docker instance in a container, and there's lots of different options because the magic is actually in the AI tree stuff is in the Java code, right? And it's portable, right? By definition, you can run Java on really any platform that has support for it. So Linux, I've never seen it on anything but Linux, but I think it runs on Windows and Mac OS and others as well, right?
We have customers running all the way from like Windows Server through Mac OS, through Linux. Speaking of operating systems, you can run it on ARM, you can run it on x86, really anything you want, honestly. So, and that's the magic of Java. Java is really nice in this regard, that it's really easy to package. It's just a single file, single jar executable. Like, there isn't a million files complete. Like, a complex installation procedure is not there. It's just, it's simple and easy to use. And again, that's because it was designed and made in that way. But so speaking about scaling, the one interesting thing here is that all of this is entirely configurable. So really how Unimus scales is each single job, each single connection to a device is a separate thread. So meaning that if you have like 18,000 devices, you probably want to run a large thread pool, what it's called. So Unimus is comprised of many different thread pools of many different sizes, and you can adjust these thread pools to increase job concurrency, which of course requires more CPU time, but also makes the jobs run faster. As you can imagine, if the average job for a device takes even 5 seconds, which is very realistic with Unimus, if you have 18,000 of those, that's like your config push or your backups would run for more than a day. So if you run 1,000 concurrent jobs, it's going to take a lot of CPU, and this is where we are talking about vertical scaling, right? But it can be scaled vertically to 1,000 concurrent jobs, and then you need a lot of CPU because it's SSH. There is a ton of encryption, then there is all of these algorithms being run, database access, or you can just split up the polling to separate polar nodes, doing horizontal scaling, and so all of this is possible. All of this is configurable, and it's actually funny because nowadays programmers, and we run into this a lot during our hiring process. Today, with the microservice, microarchitecture world, most of the programmers are used to single-thread programming. And this doesn't mean that applications in microservices run single-threaded. No, but you deal with data in a single-threaded way. So a single request all the way to the response runs on a single thread. And you might have many of these threads running concurrently, but a single request response runs on a single thread, usually. Again, not a blanket statement. There is a lot of minutiae to this, but programmers today are used to this, whereas in Unimus, we deal with concurrency, with multi-threading a lot. And we have to deal with some very hard multi-threading issues, which our programmers sometimes complain about, and it requires a different way of thinking. It's not reasonable to ask us to, for a customer to deploy 20 microservices just to run their configuration management software. That goes against it should be simple paradigm.
Yeah, it makes sense to run it that way too, because a lot of your wait time is going to be on the network device side of things. And, and so it doesn't make sense to hang up the entire Unimus process or all of your processes by putting them all under one thread.
Oh yeah.
Because even as a human interacting with a network switch, you do a show run on your switch stack with 10 members, and it's gonna take a while. So, yeah.
Yeah. So there are thread pools which pick up jobs and leave jobs. Each has their responsibility, and it makes for a really nice and scalable system, at the expense of programming being hard.
Well, there's a lot of people that appreciate that, because I've pointed a number of people towards this product to say, you haven't been doing config, collection. You should go take a look at Unimus, because it has just done the job very well for them. And it's not, you don't require to go out and go build a rancid or an oxidized system. You don't have to do all those pieces. It's pick it up, run, and things are running and up and going in minutes rather than a couple hours of some sysadmin's time. It's been very nice.
Yeah, this is the behavioral tree stuff is very interesting to me because it's a world that I don't have a whole lot of experience in, and I really enjoyed sort of having that explained to me in a way that I can understand it, because it is a very complicated set of tasks that are really broken down to make, that, like you said, they're really sort of broken down into smaller tasks that can make life a little bit easier. I think that's probably a good time to start wrapping it up. We're at almost an hour, and I want to give everybody a chance to sort of let people know where they can where they can be found on the internet and all of that, because it's that kind of world nowadays. So, Tomas, if people are looking for you out on the web and want you to explain some of this behavioral tree stuff to them in a little more personal setting, how would they do that?
So in a personal setting, yeah, right now probably not. But other than that, if you want to find me on the internet, just Google for me. I'm on pretty much all the social networks. I don't actively participate in social networks, but if you find me there and if you message me directly, I will respond. And of course, unimus.net, we have live chat. That's probably like the easiest. Just go to unimus.net, press the live chat button, ask for me, and then you will get to me.
Excellent. John, how about you?
Probably the easiest thing for me is john@osmond.net. It's something always gets to me. Email is always one of those pieces that I have relied on for so long. I have a hard time with some of the newer pieces.
No worries. Chris, how about you?
Well, if you want to find me, it's probably best to look for me on Twitter, @CrankyNetman, because, that's totally what everybody should strive to come across as, the Cranky Network guy. Also, I'm on a lot of the Network Engineer Slack channels, mainly the Network Collective Slack, but also on the Network Decode and Packet Pusher Slack channels as well. So you can find me there.
Excellent. And if folks don't know and they actually want to talk to me about something, I'm on the Twitters as @forwardingplane. I generally am on the Network Collective Slack, and I have a website. It's @forwardingplane.net. If folks have ideas that they want us to sort of try to deconstruct and talk about, send them on over. It's modem@forwardingplane.net. We'll get you to the right place, and if it's a technical topic that we feel that we can discuss, we'll do our best to do that. And we've got the new website out. It's modem.show. Check it out. It's very retro chic. And again, thanks for listening.
Thank you for tuning in to the Modem Podcast, where yesterday's modems are today's transponders. For more information or to request a topic, please visit modem.show.